My name is Harish Kripati. I'm with Virginia Department of Transportation. Uh, Today, I'm going to share some of the work we're doing in the short-term predictions from a large state DOT perspective and from a large regional perspective as well. Um, so I'm going to use a couple of things. One, couple of projects we have been working on internally in terms of crash risk prediction modeling, whether it's our internal employee safety perspective or from a crash perspective on the highways, as well as one of the largest programs that we have in metropolitan Washington region in Northern Virginia, something called Regional Multimodal Mobility Program and some of the projects. And before I get into the detail, today I'm going to probably use that RM3P projects as a use case, but some of the lessons learned and other things are based on some of the work we have been doing over the years. So when we look at traffic in Northern Virginia, which is, for those of you who do not know, in general, it's outside of Washington, D.C., just other side of the river. And when we see that, and it's true everywhere, lots of individuals making their own independent decisions collectively, along with weather, types of vehicles you have on the road, infrastructure, collectively impact the system. So in order to influence and improve, we have to collectively look at all of that as a whole. And that's what we are trying to do on this project, which you can see on the map just outside of the district. We have large metropolitan area with metro subway system, but regional buses, local buses, as well as the Virginia Railway Express, which runs parallel to I-95 corridor, north-south. We have express lanes on I-95, 495, and I-66. And so we have all modes of transportation. We have parkways, we have bike routes, and people bike from Northern Virginia to DC on WNOD Trail and some of the other trails as well. We have all modes of transportation serving the region. So those of us who are in the traffic operations business and the incident management business, we have all evolved from each agency responding to doing their own things to collectively responding with unified command. But in transportation management, each agency usually responds and deals with incidents on their own. And what we are trying to do on this program is how can we use collaboratively the real-time data that's available to improve travel safety and reliability and mobility in the region. That means it's not VDOT or Metro or local signal operator or the local bus operator, but we are all responding to the same incident, whether it happens on the highway or on the subway or on somewhere else. But all of us have the same situational awareness, and all of us contribute to moving people around the disruption. So that's the idea behind the program. In order to do that, we went through a lot of challenges of collecting all the data from all modes and all agencies into that what we call data exchange platform there in the middle that you see. Then using that data, we're trying to address on both sides of the equation of demand and supply. On the supply side of optimizing our network to get around the disruption is what we are using, that decision support tool, where all the agencies have the same situational awareness and respond to the incident collectively with single response as opposed to multiple uncoordinated responses or no response from some agencies. And so on the demand side of the equation, we have another project, dynamic incentivization, which many of us are familiar with, traditional transportation demand management. But in this program, what we are trying to do is use the real-time data to provide that real-time incentives to the folks on the road to change their behavior that moment. And that's the challenge we are trying to, take care of, where you need people to respond, and we need to provide that information, and we need to provide incentives for them to change their behavior, to reduce the demand on the system. That means they turn around and go back home, or take a metro or some other mode of transportation, change the time, go to near Starbucks using the incentive to go work from there for the next hour, to go get back on the road at later in the day. So lots of these options are available. We're working through. And then also we have about 45,000 parking spaces in the region with park and ride lots. Some of them get filled by 7:30 in the morning. Some don't get filled. Only maybe 50% of the lot is full. And also, it's not needed or necessary in our mind to count every space or count all the traffic going in and out of every lot, unlike shopping malls or the airports where people come in and out all day long. Most of the park and ride lots get filled in the morning in one end to the other end and get emptied out end of the day. So we're looking at alternative ways to collect the data without installing a lot of equipment to reduce maintenance on those operations on that equipment. We're looking at parking data collection through private sector partners that could generate the data with either limited installation or no installation of hardware. So that's overall program. I'm going to focus today on the subject of decision support system, and then move into that prediction piece of it, just to kind of, you can see the funnel. So we have within that decision support system, there are various modules. There's a rules engine, rules and logic that selects multimodal response plans based on current and future incident conditions. Then in order to do that, we need to create those cross-agency strategies and tactics that each agency can live with. It doesn't help anyone if we say you can put 10 buses on the road when the transit partners don't have 10 buses sitting in the lot with 10 drivers to quickly deploy them. So we have been working with all the 20 plus partners to create those cross-agency strategies. If incident happens on this mode here, how would everybody react, and so on and so forth. So we have developed some initial response plans. I'm sure it'll be an ongoing work, and then use that predictive engine to predict hotspots or potential for crashes or high-risk locations. What will that do to congestion? Some of the commuter parking availability and transit next stop, and the buses are coming through. When would they get to the next stop given that roadway conditions to be predicted? There is a modeling engine portion of that where real-time simulation is evaluating all these response plans that's selected through the rules, and then relative to each other, score them. So operator can pick a recommendation that works or modify the recommendation coming out of the system. There's a graphical user interface for operators to interact with the system as well. So I'm going to next talk about that prediction engine and what we are trying to do. There is that congestion prediction piece that we are looking at in 15 minutes, 30 minutes, 45 minutes, 1 hour into the future. There's a map viewer the operator can use to select the times with a slider. Also, we model that congestion based on the historical traffic patterns to forecast the traffic speeds. And that's what, when we say congestion, that's what we are using to predict that congestion. What are going to be the speeds on the various segments of the highways and arterials and all the whole network around it. We're hoping that this capability enables operations team to proactively manage congestion because they can anticipate slowdowns, but also they can see if they see the delay, is the delay increasing in the future or is it going to decrease? Now you're on the tail end of the curve. So that allows them to react much better and it may eliminate some of the surprises. Incident risk prediction, you see that it's not an incident prediction, we're predicting the risk that identifies the relative probability of incidents and on the all roadways and pick the highest probability locations and highlight them in different color. The model, again, generates in horizons of 15, 30, 45 minutes to 60 minutes into the future. And by identifying those high-risk segments, we are going to use that information to proactively deploy resources or react quickly because we're aware of that potential and get better response from multiple agencies together. So some of what I'm going to share as lessons learned here are again based on some of these. And we have deployed a pilot stage first, and that pilot, we learned a lot. As we speak, we are going through system acceptance testing for the broader regional deployment. Once we deploy that, we will see how exactly it scales from the pilot to region, and there's a lot more that we need to do to learn from those two, both congestion as well as the incident risk prediction on a regional scale. We're looking at a region that has 2.5 million people living, plus another 500,000 people coming from District of Columbia or Maryland, transiting through to work or just going through the area. So every day we're dealing with 3 million population in that geographical region that we are covering with this system. So it's a lot of information to look at and to use that in the prediction models. Again, parking availability, like I mentioned, we're looking into again the same increments because we want to see the prediction and see if we can provide that information to the commuters in advance because they are in the interstate highway somewhere trying to exit to get to the nearest park and ride lot facility. By the time they get there, park and ride lot is full. Now they park on the grass or do other things or try to find the next lot. And that create some frustration on their part. If we can smooth that out, they may end up using the park and ride lots more, and more people may use transit rather than driving alone. And also part of this, like I mentioned, we have various transit providers that they have automated vehicle locator systems on them based on their GPS. If we tie that to the traffic conditions and what we are monitoring on the arterials and interstates, what travel times we're predicting, we can also predict when that bus would arrive at their next stop. And some of the ones on the interstates, if there is an incident, it takes forever for them to get through that bottleneck. They may have to do something else. And some of them already have been doing to take them to nearest metro stop and stop the route there and turn around to come back as opposed to going all the way to the District of Columbia inside. So there are strategies that they can use if they can predict when that bus will arrive, and also that heading back to the depot to use the same bus for the second route also gets impacted as well. So we are trying to use this system to do that, to make transit more efficient. So with that said, I want to share some lessons we learned and our thought process after going through these conversations in the last few years. When you talk about the prediction, first thing comes to mind is every time I look at any financial predictions or financial advice from anyone is that SEC disclaimer that past performance is not an indicator of future results. In my mind, I'm beginning to think is, does it apply to traffic prediction and how much? We are predicting the next hour based on some of the past performance of the system under similar conditions. But in the past, many things have changed. The COVID is an example. If not, we could have built another interchange that diverted traffic some more. Traffic patterns are not constant. Our transportation system is not constant. metro service changes and bus routes have been changed and so many other things. People are moving in and out. You have a traffic mix when we talk about drivers and our users of the transportation system. Washington, D.C. region has most transient population. Many people in Pentagon come here for 2-year assignment, or many people in D.C. working from all over the world come here to work and then leave it in the various embassies. So we have uh, a population that's changing quite a bit every year. And so from that perspective, we use the data to predict something. How accurately could we do it? Are we, and that's partly what we are trying to learn. It's like uh, an example of water flow modeling. Are we trying to model individual water molecules? Are we trying to predict the flow of water as a whole? And so some of that thinking we need to have, and we look at that and we look at how granular you want that data to be in using those data to do the models. So from that perspective, target setting is really important to measure the accuracy. When we say 90%, 95%, when we talk to the engineers and others, they're all used to that 95% prediction. But accuracy, is that realistic? If you say I want to predict an incident at mile marker 10 at 7 o'clock in the morning, is that realistic? Or should we set the target, which that's where we are heading with this, with project and our work, is incident occurred in the top 10% of the segments or top 5% of the segments that we have in our system or that we predicted. That's where relative risk, and that's what we are measuring and see then how accurately this model can predict. And also the speed, one of the things we looked at speed prediction is what deviations that we're going to allow in the prediction accuracy. If you say 5 miles plus or minus, you already have 10 miles spread. And a lot of engineers want this to be exact and precise, 2.5 miles plus or minus, or 2 miles plus or minus. I'm not sure that is realistic, so we're looking at that is 5 miles plus or minus, or is it 10 miles? What is, and how useful it is. When you look at the traffic congestion prediction, how do you measure? That's the other thing we learn. If you measure 15-minute intervals throughout the day, you get a different answer on how accurate you are. Or you look at 24-hour period, the model would predict really well when there is no congestion. That will dwarf the actual incident time. When something happened, you get bad prediction. The model still could show very accurate prediction, but it's not useful to the end user. So that's something really important we learn and want to share that. So maybe any conversation on the predictions to start first on what target you're trying to get and how accurate you want that to be. How do you measure it? And then work backwards to the model development itself. And model selection, again, a lot of engineers were in the room argued back and forth on how well the vendor will have to show you how the model works, what details we need to learn about the model, how it calculates. We all grew up as engineers, doing actual calculations versus in machine learning and some of these advanced models we are using. Do we really need to understand how? Just like you ask, when you get an investment advice from your financial advisor or an engineering consultant giving you some advice, do you know how their brain truly operates, a neural network, and the brain neurons are fired to come up with that answer? Or would you look at that, what qualifications they have, what experiences they have gone through, and then make the selection? And then when they give you recommendations, they have to give you why they're making those recommendations. And so our thought process in the short-term predictions, probably we need to be open-minded and look at it differently than our traditional engineering training allows us to do. So from that perspective, we looked at a lot of models, narrow the list down to small groups, select 3 models and did a little bit more work on those, looking at that performance of those selected one, and that's what would allow us to do that. And then we could always change that model based on some of the lessons we learned from deploying that and adjust again. Again, these models drift. There's never going to be the same model that you can work on forever. So once your data changes, you react and you respond. Next year, the traffic conditions are going to, you have to continuously update those models and tweak the models and retrain the models. And that's part of what we're looking at as well. That's something we need to keep in mind. It's not just initial deployment, how well you maintain the model, monitor the model performance. Like I mentioned, a lot of data, the behavior of the driver, how do you model that in this prediction? And there's not going to be enough data or type of data you need to get started with. And data is never going to be fully accurate. I mean, that's the reality of any data anywhere else. Even the financial sector, they deal with that, or any other sector. We'll start looking at other industries, how they deal with that. So one of the lessons learned from that is we have to start somewhere with what we have and improve over time. And one of the things we are now attempting to do and understand better is the use of synthetic data technique. I'll talk a little bit about that to train the models. And the reason for that is when you do a classification algorithm and based on training that model, when there is an incident and there's a rain, or when there's an incident, you look at the data, there is a rain 10 minutes before or whatever. Now you train that model to do that. Again, every time there is rain, is the model going to say there's going to be a crash? Versus you train the model with to eliminate that bias. If you create that synthetic data or additional data set in the same stream 10 other times, the rain happened, no crash happened. Now the model may react differently than if you just train the model based on only incident data. So we're looking to see how we could create that all the data when there is an incident, when there is no incident. So the model is trained to understand the time of day to all the weather factors and everything else. And also the other thing, when you look at forecasting 1 hour into the future, incident information, when the incident happened, police report may give you really good information about the weather and all that stuff. But that may not be the one you're modeling. You need to know what happened an hour before. What is the weather forecast? You're looking at a weather forecast now. What's the National Weather Service or any other private source you're looking at is saying from now to an hour into the future. It may change an hour from now. That conditions may not happen. So now you need to go back and truly get that accurate model. For every incident, you have to go back an hour before and see what the forecast was. That's the challenge we had, the forecast availability when you go back in time to try to model that. That's where we found a lot of challenges in finding the right data. Again, these are all some of the lessons we learned going through that. So synthetic data is, again, you can mimic the real data based on some statistical models, and there's a lot of science behind it. It's published already. It's used widely in financial sector. So you can use that to fill missing data, correct the data, or like I said, sometimes you create that synthetic data when there is no incident or other non-event related information as well. So you can model better without any bias, at least reduce the bias. So that's and the other thing that I want to close out before we run out of time is that these deployments and predictions that we can do, but deploying that technology by itself or the model, how accurate that is by itself, is not an end all. Now we learn, especially when we are dealing with on our side with 20 agencies, how do people react to that? what we found when we started asking questions about what are they going to do with it, how do they use this, they're falling back on their standard operating procedures and their muscle memory rather than the information that they are going to get from the system that's not available to them today. They have not experienced that. So they cannot look into the future to say, oh, if that's available, I would react this way. That comes at an operator level after going through some growing pains. And so we need to focus on the deployment side. How do we train people? How much in advance you bring them to the table to have those conversations? You can give them the prediction. If they don't know how to use it, they don't deploy, they don't use it because they don't understand enough of it, because you have not developed that user interface and training pieces, then it's not going to be successful. So the process is, like I said, we need to work with them in changing the SOPs to incorporate how do they use this prediction information in making their decisions in collaboration with others. That's again a big change from the people perspective as well. Right now, they're making their own decisions. Now they have to collaborate with somebody. So, and the tools and technologies, they're getting better every day. What we started on this project 2019, when we conceptualized this, to today, the world of technology changed by leaps and bounds. If I were to start today, I might have done it differently, but we need to continue to evolve with the technology, with the tools, and incorporating that from the technology perspective. I think Kelly talked about how do you integrate that into your own traffic management system, or is it a separate system sitting on the side? A lot of those. How much autonomy are you going to give to the system versus human in the loop? A lot of those conversations are important that we need to have before you deploy or think about deploying any predictive algorithms in the traffic management. So I think that's my last slide, and here's my contact information. I'm going to turn it over to, I guess, David to moderate the Q&A.